Okay, last time we briefly introduced difference frequency generation, and then difference frequency generation, DFG. And then the reason that this nonlinear process is important is because unlike some frequency generation, difference frequency generation can amplify one of your input line. The solution, okay, is not a sine or cosine, but by simple analysis, you will see that, okay, it's actually exponentially increased. So this week, we're going to formulate, okay, the math of this DFG process, and then show you how to make it into first amplifier, and then second into a laser oscillator. Okay, and these things, I think, they were mostly discovered in the 1960s and 70s, and now they are commercialized. You can actually buy parametric amplifier. Last time we briefly said that the difference frequency generation, the amplification caused by difference frequency generation is also called parametric amplification. So nowadays you can actually buy parametric amplifier and also parametric oscillator directly from the market. Okay, so okay, so the equation that we're going to use is fairly straightforward. As you can see here, is that there are also just 3 waves in this interaction, omega 1, omega 3, and then omega 2 is at the frequency difference of omega 3 and omega 1. So you can kind of think that the equation of difference frequency generation would be similar to some frequency generation. Okay, so we'll be focused on the difference and where does it come from. And the equation that you would like to use here again is the equation for nonlinear interaction. This is in page 30 in the lecture note. Okay, this one you guys have seen too many times probably. And then the nonlinear interaction, again, this is a second order nonlinear effect. So you have chi2 and then E squared here. And again, to simplify everything, we assume that all the wave, their polarization is pointing towards the, let's say, x-axis, so that you can drop the vector here. Okay, so the nonlinear polarization, you can simplify it into the direction that we assign. And then again here is E1 plus E2 plus E3 and their conjugate. Okay, and here just like some frequency generation, E1, E2, E3, it should be followed by exponential frequency term and then the kz term, the phase term. But for the first step calculation, we just drop them. Okay, we can add it back later. And well, we have done this before, right? How to expand them, and the trick is that you only pick up terms that has frequency of omega 1, which is also omega 3 minus omega 2, okay, and then omega 2, which is frequency omega 3 minus omega 1, and then omega 3 is omega 1 plus omega 2. All right, so you only pick up these terms because they are the terms that participate in this in this difference frequency generation. Okay, and now you can easily tell. Okay, this one will go to. think here there's no vector. Okay. So what is the process? What terms correspond to omega 3 minus omega 2? Right? It's E3 times E2 conjugate. Right? This is omega 3 minus omega 2. And then it's very easy to see that there are two of them. It's E3 times this one, and then this one times this one. Right? So you always have a factor of 2 here for any of these cross terms. And then the same apply to omega 3 minus omega 1. That will be 2 E3 E1 conjugate plus 2 omega 1 plus omega 2. So it's E1 E2. And then the conjugate of all these three terms. Okay, so if you plug this back in here, and then add the frequency components and then the phase components, and then what you can do is that you can pick up, and then you can arrive at 3 different equations corresponding to 3 different frequencies. Right. So you guys are fairly familiar with this in the sum frequency generation, so we'll just skip to here. Okay, the first equation is about wave, is about frequency component omega 1. Okay, and this is I. Omega 1 square. Okay, the 2 cancel with the 2 here, so there's no 2 factor here. Okay, 1. E3 E2 conjugate. Okay. Okay, and the same apply to the second equation. You guys can see all this in page 30 in the note. And something that you can obviously try to do is to prove that, again, these 3 equations have satisfy energy conservation. Okay, this is E1. Okay, so these are the 3 coupled equations for omega 1 wave, omega 3 wave, and omega 2 wave. Okay, and then apparently one thing that we want to do is to assume that we have phase matching condition, right? Because we don't want to carry this exponential, the phase term everywhere, and then we would just leave to the experimentalist. Okay, we say that we can do this, and then we ask them to do it. Right, so let's assume that we have phase matching. Okay, assume phase matching. Okay, which means the momentum is conserved in this difference frequency generation. And then you arrive at this equation. Okay, again, very similar to the sum frequency generation. The only difference is here, like if you look at, if you focus on equation 1 and 2, what you see here is that equation 1 is not proportional to E2, but instead it's conjugate. Okay, so later, okay, this will play a role. Is because then if you want to plug in this to here, you need to take conjugate of this equation. and that will change sign of this I. Okay, so that will change the behavior from sine cosine oscillation to exponential growth. Okay, so this is where this is mathematically okay. Where's the difference between some frequency and difference frequency, and physically, okay, from a physics picture, we have already explained, okay, why one will grow, one will oscillate. Okay. Now, another approximation we're going to make, just like some frequency generation, is that we're going to assume that one of the wave is very strong as a pump, right? And then we can assume that it does not change in the crystal. And apparently, okay, one good choice would be E3, right? E3, because E3 generate omega 1 and omega 2, right? So omega 1 and omega 2, they increase together. And omega 3 is a wave that, supply the photon to them. So it makes sense to assume that you have infinite amount of supply, right? So you can assume that E3 at any position Z is much, much larger than E1 and E2. Okay, so that this equation, the differential equation of E3, okay, this on the right-hand side is very small, right? So approach to 0, then your E3 doesn't change, so that you can assume that E3 at any point in the crystal is equal to the input at the input port. Okay, so if we make this assumption, then we can eliminate this equation, okay, because E3 do not change. And then we can change E3 here from a function to a number. Okay, from a function to a number. And this is usually in an experiment. Usually people are operating under this condition. Okay, your pump is much, much stronger than the two wave. Okay, one is amplified, the other is generated. Okay. Now we get to here. And so one thing that just like some frequency generation, what we can do is that we don't want to carry around all this, all this coefficient, right? It's a lot of them. So you can assume that this is K1, capital K1, okay. This is capital K2, okay. So in the note, I include I, okay, into the K1 and K2, and that's not a good idea. So because then you have to, because then you can easily lose track of whether K1 is a real number or imaginary number. So here, what we can do is that we leave the I in the front, okay, and then K1, E2 conjugate Z. This one is also leave I, okay, and then K2, E1 conjugate Z. Okay, so this is another set of very typical coupled equation. Okay, where E1 is coupled to E2 conjugate, and E2 is coupled to E1 conjugate. Okay, and when you have this, what you usually do is that, for example, if you want to solve E1, okay, E1 is the input line, so if you want to solve E1, then what you do is that you take differential of the first equation, so the left-hand side becomes second-order differential equal to I K1 okay, differential of E2 conjugate, right? And how can we get E2 conjugate differential? Right, we use the second equation and then do a conjugate of the entire equation. Right. So when you do a conjugate of an entire equation, what you do is that you do conjugate of every complex number or every complex function. So here you have E2 conjugate Z, okay, equal to I will become minus I. Here, okay, you need to be paying attention here. K2, let's see. K2 is not necessarily a real number because E3 can have a phase, right? E3 can be a complex number. Although in experiment, last time we have already learned there's a degree of freedom, right, for you to choose of the original phase, right? So typically people choose E3, the phase to be 0, and this is a real number, okay? But then without losing generosity, we just keep K2 as a complex number, okay? So K2 conjugate, and then E1, right? E1 conjugate, and then you do a conjugate return to E1, right? So now if you plug in this equation to here, you will naturally get an equation between E1 second order differential and E1, right? So you get equal to I times I is minus 1, and then there's a minus sign, so cancel each other, so it's a plus. So it's K1, K2 conjugate, E1. Okay, E1. And then you can do the same, but then to the second equation, right? You can do exactly the same thing, and then you will see the equation for E2. I think it's simply a reverse. Strange, I don't have it here. Anyway, let's see. I think you can kind of see the solution should be K1 conjugate, because you need to take conjugate of the first equation, plugging into the second equation, so it should be K1 conjugate K2, and then E1, E2. Okay, you guys can check. For some reason, I don't have this on my note. Okay, then a very important thing that we need to figure out is that is K1, K2 conjugate this number here. Is it a real number, imaginary number? If it's a real number, whether it's positive or negative, right? Because that would affect your solution. So if you take a look here, then all of these coefficients in the front, they're just real number and positive, right? They're just coefficient. So the only thing that really matters here, okay, a lot of number is E3 0 times K2 conjugate will be E3 conjugate. Okay, so you see here that no matter what phase you choose, K1, K3, K1, K2 conjugate always give you a real positive number, right? So that's actually one of the reasons why we didn't assign a phase here, because it doesn't matter. So you could leave that into E1 or E2, right? Because the phase of E3 doesn't matter, so that you can use that degree of freedom and then to assign a initial phase to a wave that matters more, right? E1 or E2. Okay, so what we can do is that we can define, okay, since we now know this is a positive number, we can define it into gamma square, right? Gamma square. And gamma is a real number, and gamma square is a positive number. Same, you can check here is that these two are equal to each other. Okay, so gamma 2. Okay. So, let's see. Any questions here? Okay, I guess we can move these two equations to here because they're fairly short. Okay. Now, solution to this is quite obvious. You want the second order differential to be the function itself times a positive real number. Then the solution, okay, one possible solution is E gamma z, right? If you do differential, gamma came out once, and then twice differential, gamma came out twice, right? So gamma squared in the front. The other possible solution is E minus gamma z, right? Because then when gamma minus gamma z come out twice, the minus sign cancel each other, right? So these two are the two possible solutions, and then so is their linear combination. So from here we can write down the general solution for E1 and E2 is A1 gamma z plus B1, and then E2, okay. So see that there's an exponential increase term and then also exponential decrease term. But then because they are summed together, right? So when this exponential decrease becomes very small, you can start to neglect it, and then it become purely exponentially increasing term. And the second thing you discover, okay, the observation is that E1 and E2, when they exponentially increase, the exponential rate is the same, gamma and gamma here. And that totally makes sense because they are co-generated, right? The omega 1 and omega 2. Okay, so to solve the solution, okay, A1, B1, A2, B2, this coefficient, again, what you can do is you can use a boundary condition, right? So boundary condition is that at this input port, something you know is that E2 z equals 0 is 0. Right, that's the very first boundary condition. And then E2 as 0 is equal to A2 plus B2. Right, A2 plus B2 equals 0. Okay, meaning that B2 equal to minus A2. Right, so this part is A2 E gamma z minus E minus gamma z. Okay, and if you guys are familiar with hyperbolic functions, this is actually a sinc. Okay. By definition, okay, this is the definition of this function. And also you can use E1 as z equals 0 is a number, right? It's a number. You have an input here. And also that equal to A1 plus B1, right? And that's it. There's no simplification there. And again, that's not enough because for second order differential equation, you need two boundary conditions per equation to get all the coefficient. And the other boundary condition is that you have partial E1, partial z. Okay, this is the I K1 E2. Right? We just looked at it this a few moments ago, and at z equals 0. Okay, also satisfy this. And at k equals, well, at z equals 0 at the initial port, we know that E2 is 0, right? E2 is 0, so that okay, this is 0. Okay, so differential of E1 over Z at z equals 0 is 0. And if you do that differential, you will see, okay, gamma came out, and so it become gamma A1 minus B1 equal 0. Okay, equals 0. So that means A1 equals B1, right? And so this is simplified to A1 plus, okay, so this is a cosec function, okay? So, and you can plug this back in here, equal to 2A1, okay? And that, so A1 is half of E1 0. So here clearly you will get, okay, E1Z equal to, no, okay, E1 0, okay, and then gamma Z plus minus gamma Z equal to E1 cosec. Okay, cosec at 0 is 1. Okay, so this is the first solution. And then again, you have to use the second one. That's the partial E2 partial Z IK2 E1 conjugate 0. Okay, and E1 at 0 is a number, right? So what you end up with here is that you have to do a differential on this, plug in z equals 0, and then let it equal to this number. Okay, so it's some trivial calculation, but then it could be quite lengthy. Okay, so I'm going to skip it here, and eventually the result. Okay, eventually the result would be E2 so this will give you A2, okay, and then you can plug it back in. Eventually this will give you I and 1 omega 2 and 2 omega 1 E1 conjugate 2, okay, and then you can also reduce this part into the hyperbolic sinc function, that is okay, this one. So now two comments here, right? So the first is that where does this coefficient come from? Okay, this coefficient actually looks very, very similar to the sound frequency coefficient, right? So what this does is that it's actually a prefactor here to guarantee that the number of photons generated in E2 is the same as the number of photons generated in E1, right? And this N1 omega 2 and 2 omega 1 is just coming from okay, the power of your wave divided by h bar omega, okay, is the number of photons in your system, right? And the power of the wave has n1 in here. Let's say p1 omega 1. So you have n1 here, you have omega 1 here. So that's why you are n1 divided by omega 1, and then the reverse is omega 2 divided by n2. Okay, and this is where this coefficient comes from. And the second one you look at here is that the phase of E1 actually matters, right? Because it determines the phase of E2, right? And then there's a conjugate here. So for this system, if you want to get rid of the free parameter of the phase, one thing you can do is that you can define the time 0 point such that the E1 0 is a real number. Okay, then you can get rid of this conjugate. Right. So here, instead of defining E3, the pump, right, you probably would prefer to define E1. Okay. And it's quite clear here now that both E1 and E2, okay, they grow with Z. Okay. So for E1, it starts from E1 0. Right, and cosec at z equals 0 is non-zero, right? So, well, it's cosec at 0 is 1, right? So you start with E1 here. Let's say this is power. Okay, you start with a certain power and then you grow. And as z increase, okay, this term will be dominated by the exponential increase. Okay, the exponential decrease will approach 0. So when z is very large, both E1 and E2, okay, they approximate to exponential growth. Okay, and the second one is E2. Okay, this is P1. Okay, so as P2, the P2 of course start from 0 because there's no input of omega 2 wave. But the thing that you need to be careful about is that the growth rate in terms of power is not, they two does not equal to each other, right? Because what's equal to each other is the growth rate of the number of photons, right? So if your omega 2, so in this case you see that P2 growth rate is higher than P1. So if your omega 2 is larger than omega 1, then each omega 2 photon actually carries a little bit more energy than omega 1, then the rate of growth of P2 is larger than P1. And you might wonder, is it possible at some point that P2 is larger than P1? That's totally possible, right? That's totally possible, okay? Especially if initially your P1 is very small, okay? Then you can take over, okay? Any questions at this point? Okay, so this is parametric amplifier. Okay, as you can see that P1, okay, is generated. P1 is amplified, and let's see, another thing here is that if you check here, P1, the omega 1 power is amplified. But what's also equally important is that the phase of the omega 1 wave is preserved. So whatever phase you have in your E1 input, at the output is the same phase, right? So this is a coherent amplification process. Okay. Let's see. Okay, so for someone who is working, in optics or are interested in optics, whenever you see an amplifier, the next question is always, can you turn it into a laser, right? So a laser is probably the single most important thing in optical research, and I'm not sure how many of you actually learned the basic principles of laser, but it doesn't hurt to repeat here. And actually, in UVA qualified exam, if you select photonic as your area, the very basic question that we always ask is, can you tell us what's the basic structure of a laser, and then what's the requirement to start a laser? And you'll be surprised how many people fail. Okay, and so here, before we start going into making a parametric oscillator, which is using parametric amplifier to make a laser, we'll probably start a little bit of introducing the very basic idea of laser itself, right? So a laser, well, by the way, laser is invented in 1960. Okay, so the laser, the basic principle of a laser is that you have an amplifier inside. Okay, and think about it. If this is just an amplifier and light goes through from the left to the right, right? The thing it does is that it will amplify the light, right? That's all it does. But think about it. How to make this effect, multiple times stronger, right? The idea would be you put a pair of mirror, right? You put a mirror here. Let's say you first put the mirror here. And then this light is reflected and going back to the amplifier, right? So in this way, your light is amplified twice, right? It's amplified twice. So it's twice stronger, right? And then you can actually make it even better, is that you again add another mirror here. And so when the light coming back, and then you reflect it back again, right? So the light is circulating inside this, what we call the optical cavity, right? Or Fabry-Pro cavity in this case. And then the light coming back and forth, and then being amplified for many, many times, okay? And so you would think, okay, then you just, make this an extremely efficient amplifier. But what's interesting here is that you can think about a scenario now. Okay, you can think about a scenario now. Suppose in this system, let's say amplifier, suppose there's one photon, okay, right? This is a very common situation if, let's say, the amplifier is coming from atoms, that the electron in upper level, when it come down to lower level, emit a photon. Okay, this is one type of amplifier. For example, our fiber amplifier. Suppose now you charge your amplifier. Okay, put a lot of electron into the upper state. Right, and at this point, you can think about it. At this point, let's say there's no initial photon. Right, you didn't input any photon because whenever you input a photon, it becomes an amplifier. Right, so let's say you don't input any photon. You just put an amplifier, a pair of mirror, and then you make the electron in the amplifier all go to the upper state. Right, and you guys know that there's spontaneous emission. Right, so at some point, one of the electron will come down to a lower level and then spontaneously emit a photon. Okay, so this is very different from amplifier itself, right? Amplifier, you need an input. Here it's like we have a spontaneous emitted photon. Okay, and this photon, okay, let's say emitted here, from here, goes through the amplifier and then being amplified, let's say to 2 photons. Right, and then reflect by the mirror and coming back and become 4 photons and keep going, right? So then what it looks like is that this, okay, amplifier with a pair of mirror can self-start to oscillate, self-start to emit photons, right? And then that become a laser, right? A laser is a device that emits very highly coherent photons, okay? And you might think, okay, then is there a condition for this, right? It's very obvious, the condition is very obvious, is that if the light, okay, let's say now you have 1 photon from the left, okay, when it finishes one round trip, meaning that it goes from meaning that it goes from the left, goes through the amplifier, hit the mirror, coming back, goes through the amplifier, hit the mirror, and then reflect back, right? It finished one cycle. When it finished one cycle, if you start from one photon and then you finish one cycle, the number of photons here should be more than one photon, which means you have a net gain, right? So if you have gain in the amplifier and then minus your loss, okay, the loss can be introduced by the mirror, which is not perfect, or can be introduced by a lot of defect in your system. So gain minus loss, if it's larger than 0, meaning that you have a net gain in your system, one photon finish one round trip can give you more than one photon, then this process can, can cascade, right, and then generate more and more photon until it reaches an equilibrium steady point. Okay, so this is, how a laser works and how you start a laser, and then for a laser, a very important concept in the laser is what is the threshold. Okay, there's a gain, right? What is the threshold for the gain? Right, you have to achieve certain gain for your laser to start. Before that, your laser only emits spontaneous photons, and then because the gain is not larger than loss, and then you won't see any active light. Okay, and the threshold, although we say, okay, it's gain, but then in real measurement, the threshold can be expressed in many different forms. For example, for semiconductor lasers, what you do is you inject current, for example, into a p-n junction, then move your electron to the upper level, right? So in there, what people typically measure is that you have the laser power, and then the x-axis is the current, right? And then below the threshold, you have almost 0 output, and then above the threshold, okay, you have laser power increase, okay, with your current. And also there are some other type of lasers. For example, the first few lasers demonstrated they are not solid-state lasers, but they are gas lasers. What they do is that they actually have a light bulb shining, okay, the gain media, and then the gain media absorb those light, and then so it's a 3-level thing. We're not going to talk about here. It's in Joe Campbell's class. Okay, so okay, instead of using a current, they will use power. Okay, power versus power. Okay, this is the power of the pump light. Okay, so nowadays for some fiber amplifier, for some fiber lasers, okay, inside the pump is still optically pumped. So, for example, the EDFA you guys might use, okay, in the future, a type of amplifier, very popular in telecommunication system. Inside is actually a light pump, okay, instead of semiconductor pump. And which pump you use or whichever gain mechanism you use depends on your application, your requirement for power, your requirement for noise. Okay, so we're not going to get into the details. Okay, so the takeaway here is that a laser is composed of amplifier, okay, that amplifies signal, and the feedback system, which is typically a pair of mirror that have your photon go through many cycles of amplification, and then a key figure of merit in a laser is its threshold. Okay, what is this threshold? So now, since we know all this now, we can easily turn our parametric amplifier, okay, into a parametric laser or parametric oscillator. Okay, so what we can do here is we simply say this is DFG. Okay, or parametric amplifier is usually PA. Okay, parametric amplifier. Okay, so you have a parametric amplifier inside here. Okay, that came from the difference frequency generation, your pump, what is a pump in this laser? The pump is omega 3, right? Omega 3 is the part that supply photons or supply energy into your amplifier. So P3, usually there are two different ways to do it. One is that your P3 can come from, come from another direction that's not on resonance with the with your cavity, or it could just be injected. Or it could just be injected from one part of the cavity, right? The mirror is never perfectly 100%, right? You can actually change the reflectivity and transmission by changing the coating, on the mirror. And actually, you don't need to know how to do this. There are numerous companies help you to do this. You just give them the number you want, and they will do it. Okay, so there are two ways that you can inject this. And then different from the different frequency generation, you now don't need to input a light of omega 1, right? Because this is a laser, Omega 1 will self-start, will self-start. And so let's make it a little bit simpler here. So the mechanism here looks fairly identical to a typical laser system, right? Somewhere, let's say, assuming somewhere, magically, a laser of omega 1 photon appear, then what it would do is that through this parametric amplification process, it will generate another omega 1 and then omega 2, right? And then it will cycle around in this cavity, and omega 1, both omega 1 and omega 2 will be amplified, and spontaneous start. The question, I want you guys to think about, I'm not going to give the answer directly here, but to think about is where does the omega 1 come from? Original omega 1 come from? We don't have, remember in parametric oscillation, your material is always at its ground state, right? In the amplification process, there's never an electron really going to the upper level, right? So where does the original omega 1 come from? And the fact that the origin of this omega 1 is different from a conventional laser, make this parametric oscillator actually a quantum device, not just ordinary classical laser. And this is parametric oscillation. Parametric oscillator is actually nowadays a very standard way, to create quantum light in, for example, in LIGO, in gravitational wave detection. There's this to help improve the sensitivity of LIGO, and also people use this for quantum computing. At the end of this section, we would kind of unveil the answer, and then also we need a little bit of quantum optics knowledge, which we will talk about in the second half of this semester. Any questions about the basic mechanism for parametric laser? Now let's talk briefly about how to write down equations for laser actions, right? For laser actions, and it's actually quite different from, well, it's similar, but there's significant difference from an amplifier. The first thing is that we can take a look at this. We first, of course, take from what we already know, right? We can assume that there's, again, we assume E3 is much larger than E1 and E2. That's a pump. We want to make things simple. So assuming that, and then And then we assume there's E1 wave and E2 wave inside the cavity. Okay, inside the cavity. Don't ask where it come from. Later we'll know. Okay, assume they're there. Then for the wave, okay, to travel, let's say you still have Z here, right? There's a from previous nonlinear equations, we know how to solve the equation. Okay, once we know the wave at the starting point and then it propagates along Z, right? We know that. So we can write that down. Let's say partial E1 Z, partial Z, and then there's the coefficient, okay. K1. Right, this is the part that what happened inside the parametric amplifier, right? Just standard difference frequency generation. And this part will give us gain, okay? This part will give us amplification. So the question is, okay, where's the loss? How to add the loss into the equation, okay? And we actually know that, you know, how to write down loss. I think you guys all seen it before. Loss is simply if you have a wave, and then, okay, and then the amplitude of the wave, okay, decrease linearly. The rate of the decrease is proportional to how much light you have. And then this will give you an exponential decrease. Okay, so this is the way that you know, the light is being absorbed. And I think in the homework you guys kind of work a little bit on why. Okay, there's a factor of 2 here. The reason is fairly well. The reason is that the when people measuring loss, they don't measure electrical field. They measure the power. Okay, and the power is the square of your electrical field, right? So there's, if you write down power as P Z equal E minus alpha Z P0, right? And then you reduce it to E, then there's a factor of 2 here, okay? So this is just to make our measurement. So that way you can tell, okay, this equation is actually coming from the measurement people see here, okay? So here what we can do is that, okay, we now know this is the loss, so we can add a loss term here. Okay, and because this equation is about E1, right, differential of E1, right, so E1Z, okay, this is loss. And you can do the same to equation 2. Okay, E1 conjugate, and then also loss for E2 mode. Okay, so by doing this, we introduce, well, we already have gain from the parametric oscillator, parametric amplifier, and now we introduce the loss, right, from this term here. Okay, and the next thing that we actually need to think about is that, do we really care about Z in the laser? The equation is about Z, but do we really care about Z in the laser? When you turn on the laser, what really matters is how much light is being outputted from here, right? What's the intensity inside the laser, and what's its spatial distribution actually doesn't, it's not an important thing to us at all, right? So for a laser, the equation, okay, the net result is that we don't really care about this. We don't care about this. We care about this, E1T. We care about when you turn on the laser, does it turn on immediately? Okay, does the power fluctuate with time? Right, this is how when you turn on the laser pointer, right? And then if you see, okay, the power change with time, that you care a lot, right? So what we need to do, okay, for laser, what we need to do now is that we need to convert the equation from Z to T, right, from Z to T, okay? And I think we can finish this in 5 minutes, and I will let you guys go at 12, okay? And the way to do this, okay, the way to do this is extremely trivial, okay, is that we know there's a relationship between Z and T, right? So for example, you start a wave at this point, okay, you can call it Z equals 0, and then let's say you now want to check the point as Z equal L. And you can change that. The wave at Z equal L is actually the same wave as T equal to L divided by the speed of light, right? Because after this time, your wave propagates to L, right? So there's a one-to-one correlation between position and then your time. Okay, so that's the way that you can think about it. So the way that you can kind of convert Z to L is that you can, well, Z and T is that you can write down Z as speed of light times the propagation time. Okay, speed of light times propagation time. That means when you propagate to here. Okay, and then you might wonder, okay, but what about this back and forth, right? So what you can do is imagine, okay, what this is equivalent to is that there's no mirror here, but then there's a next parametric amplifier there. Okay, so light coming on here and then reflected back going to the parametric amplifier is equivalent to light coming here and not reflecting, keep propagating, but there's a next parametric amplifier here. Okay, so and then so the way that you can think about it is okay, this is 0 to Z and then Z back to 0, but then you can kind of switch and patch here is that 0 to Z, Z to 2Z, Z to 2Z to 3Z. Okay, so this way you can kind of these two systems are equivalent, okay, and that's why you don't need to worry about when T, okay, is too large, then Z is larger than the length of this, whether this equation will work or not. Okay, so now if we, plug in this to here, what you'll have is E1T, okay. Notice here is that Z and T are just a symbol in the E1 and E2, so you don't need to carry this coefficient here, okay. Partial T, okay. Here you plug in Z divided by N T here, and then there's a coefficient coming in the front. And then, so I'm going to leave all those, move those coefficients to here, and then they cancel with this one. So this will become, let's see, I omega 1 squared, okay, chi 2 CK1. Okay, CK1. And E3, 0, E2 conjugate T. Okay, this is the first term here. As you can see, there's a C, there's a refraction index. What it does is that when it comes to here, it cancels out with this term. Okay, this gives you a speed of light and then speed of light here. And I think I did, yes, I think I did assumption is for simplicity, I assume the refraction index is 1. Okay, and you can carry that refraction index. It doesn't change anything in physics. And then the second term here is alpha E1, right? So here alpha will become alpha when you plug in here will be C divided by N, alpha times C divided by N. Okay. Okay. So so what it is here is that here it only changed from one parameter to another parameter, right? So all you need to do is to define a parameter that makes sense to you. So what people have decided to define is this, okay? It's tau, okay, 1 over tau. So what this is that if you don't have gain, okay, then you just have this exponential decay, then the solution would be e to the minus t over tau e1. Okay, so this is like the half-lifetime of your decaying system. Okay, and you have the same for E2, which you guys can see in the in your note. And then one thing I want to ask you guys to think about is that can we solve this equation analytically? Okay, is there a way to solve this equation analytically? And if not, why? Okay, if not, why? Okay, and that is all for today. Sorry, I have to go to another meeting and talk to you guys on Wednesday.